wanted to formalize that equation just a little bit, we'd say Q is equal to n over 6.24 times 10 to the 18, where n is the number of elementary charges, and 6.24 times 10 to the 18 is the size of a Coulomb in terms of the number of particles per Coulomb. And as we continue down the page here, sometimes people don't talk about it as how many charges there are per Coulomb. Sometimes they swap around the idea and they say, well, how many coulombs is one charge? Well, that seems like a weird thing to say. I mean, like, you don't talk about that with eggs. I know with eggs, I say, well, 1 dozen equals 12 eggs. But one egg, isn't one egg 1/12 of a dozen? And that seems like an odd thing to say. Not dozer, dozen. That seems like an odd thing to say, but that's exactly the kind of thinking that we've got going on when we do what we've got on the left-hand side of the page here. We're saying that Q is equal, for one electron, Q is equal to one elementary charge divided by 6.24 times 10 to the power of 18 electrons per Coulomb. That means that one elementary charge, one electron, is, the negatives because it's a negative charge, but it's 1.6025 times 10 to the power of negative 19. You notice when I'm talking about one egg, it's 1/12 of a dozen. That would be like 12 to the power of negative 1, right? Here we're talking about 1.6025 times 10 to the negative 19. So this is going to be a really small number, just like 1/12 of a dozen is a small number. Am I kind of selling the idea? That negative exponent on the 19 means that this is a tiny number. Yep. Oh, because electrons have a negative charge. So if I wanted to talk about what the charge of one electron is in terms of coulombs, this would be the numerical value. That would be the fraction of a Coulomb we're dealing with, but its charge would be negative, whereas a proton would have a positive value. So yeah, we have negative and positive charges. Unlike eggs, we don't have negative and positive eggs, right? I mean, yeah, the anti-egg. I don't know what that would be exactly. You guys ever had a 100-year-old egg? In some ways, I feel like that's the anti-egg. I don't know. Pickled eggs are fun, though. Anyway, I got a jar of pickled eggs at home. I'm just bragging now. Bought it at Costco. So what we're saying is that one electron has this charge magnitude and is measured in coulombs. And we even say that this is the way we talk about electrons in SI units. We talk about them in terms of their value as a fraction of a Coulomb. A Coulomb is a System International unit, international system of measure. Now, I'd like to take a look at a circuit. And I have this circuit that's kind of been defined here at the left-hand side. It's a basic circuit like what we've been talking about before. It's got a light bulb, it's got an ammeter, it's got an electrical source, and we're going to run 0.5008 amps. So not quite the same current as the one on the previous page, ever so slightly more, and I'd like to run it for 10 minutes. Well, if I run this thing for 10 minutes, 10 times 60 seconds, that means 600 seconds have gone by. I'm going to say that the 0 on that 60 is a significant value. So right up to that last 0, we'll say is significant. So that means 600 seconds go by, and all the while, 0.5008 amps are running through it. And if I wanted to calculate how much charge flows through this circuit, I could go through the process. I could say, okay, how many coulombs flow through the circuit? I need to know the amount of current, the flow rate. I need to know how much time goes by, and I could rearrange I equals Q over T to get Q all by itself. If I do that, and don't worry, I'll pause because I know I'm going faster than some people are writing. This is always the issue with slideshows, right? If we do that, then we can flow in, or we can sub in our current flow rate, 0.5008 amps, times the time, 600 seconds, And if you're worried about whether the units are going to work out, you never write amp seconds. Remember, an amp is defined as coulombs per second. So that amp is actually coulombs per second in disguise. So when I multiply coulombs per second times seconds, the seconds cancel out, and we're left with coulombs for the units. And it ends up being about 300.48 coulombs, and rounded off to 3 sig figs, that gives us 300 coulombs. Follow-up question might be, how many actual electrons flow through the load? Because what we've got is the number of coulombs, but a coulomb, there's not 300 electrons. Remember, a coulomb is kind of like that idea of the dozen, but applied to electron quantities, right? So if I've got 300 of those electron packages that we call a coulomb, we don't have 300 electrons flowing through. We have 300 times however big a coulomb is. You guys give me a nod. You guys need like a few seconds to catch up. Have I gone too fast? Sorry. Yeah, absolutely. A little bit of processing time here. I'd say, like, as we look at this, you guys believe that, I mean, honestly, when I've taught different pathways for grade 9 science, there have been semesters where I have a really keen group of grade 9 science kids, and I've just taught this idea anyway. Especially, we've kind of finished the basics of grade 9 science. This is an easy one to bring out and say, hey, what is current really? You believe a grade 9 science kid could handle this? I think for them, the biggest challenge is dealing with the scientific notation part of things. For you guys, though, you should be pros at that stuff. Here's a quick little historical aside. Which charge was called positive and which one was called negative was totally arbitrary, and it was arbitrarily made before we really knew which charge was mobile. I think I said that already. But this is the problem when chemistry and physics are kind of at the same cusp of understanding the way the universe works. I think we're kind of always in that stage now, right? Things are moving so quickly. This was over 100 years ago. I think it was, maybe I'm wrong on this, I think it was 1897 that we got like solid evidence for electrons being a thing. And it wasn't until somewhere, I think like 1907, that, what was his name again? Millikan calculated the charge of an electron. So I'm like, this is really is like our great grandparents kind of territory, right? But still cool that this is stuff that was figured out during our great grandparents' day. I guess depending on the lengths of these generations in your family, it could be your great great grandparents. But anyway, you know what I mean, right? Still not within living memory, probably, unless we got some 140-year-olds kicking around. So we got this follow-up question is how many electrons flow through the load? Well, we have this equation, n is equal to q times 6.24 times 10 to the power of 18, which is actually just, or I'll pan up the page a little bit, we're just taking this equation from before and isolating for n. I know, it's a flicker thing. So if we isolate for n, then we end up getting this equation down here that I just brought up. N is equal to q times 6.24 times 10 to the power of 18 electrons per coulomb. Then we can sub in our values. We got the number of coulombs that fly through this circuit. We got this, we'll call it a constant, 6.24 times 10 to the 18 elementary charges per coulomb. Notice that the coulombs are going to cancel out. And we say, okay, well, the number of electrons or the number of elementary charges that went through this load, this light bulb, was this number, 1.8749 times 10 to the power of 21 electrons. Holy smokes, that's a lot. And that's why we don't count them by the individual. Like, talk about sticker shock. Isn't 300 a lot more easy to process for us? Same reason I buy eggs by the dozen. One time I watched a guy down at Costco. He had, you can buy eggs by the 36 pack down there. He had a 3 dozen egg package, and he had filled up the shopping cart. And as I was looking at this guy wheel these things out, first of all, great price. Secondly, I hope this guy owns a restaurant because that's a lot of eggs, right? Like, or else he's just having everybody over for omelets, and I mean everybody, right? But like that's a lot of dozens, and it makes sense that we don't usually count things by the individual. We count things by the package. In this case, packages of Coulombs.
Yes, he has like something thousand eggs.
What's that?
He has something thousand eggs in there in that shopping cart.
Yeah, a Coulomb of eggs. If you had a Coulomb of eggs, oh my gosh, trouble. Think about how many chickens there could have been if you hadn't eaten their. And never mind. I'm talking about eating their children. Anyway, if you really wanted to get into the light bulb, and I used to do this dissection years ago with the pathway that's going to college as opposed to the pathway that's going to university, I would take a light bulb, we'd take an incandescent light bulb, and we'd smash it inside of a paper bag. We do a light bulb dissection. And I'm not going to do a light bulb dissection with you guys. You can smash a light bulb yourself, like make sure it's not working anymore. It's like burnt out. But if you smash an old light bulb, what you're going to find is all these structures. You'll end up having an electrode that's actually right there in the bottom of the light bulb. There'll be like a button that sticks out. And then you'll see in almost every light bulb an insulation rubber ring that surrounds that. Now that little button, that electrode, is connected to a wire that travels up through the center of the light bulb, and it's encased in glass. It's encased in glass because glass is an insulator. And then it gets attached up to, almost looks like an antenna on one side. Then there's a filament, or in a more modern light bulb, it would be an LED. But it's the same principle anyway. That filament or that LED is going to dissipate electrical energy, and then the electrons flow back down the other side, and they actually flow out through, you know, the threads that you screw into a light bulb socket? That's a part of the circuit. It's not just like to fasten it in place. They make contact with the edges of the light socket. And so electricity goes up through the center. Look inside of a light socket one time. There'll be a dot in the middle that's made out of metal. That's the entry point for the electrons. Then it'll travel up through the center of your light bulb. It'll go through the filament or LED. It'll come back down again where it's soldered to the threading on the edges of your light bulb, and then it returns back to the circuit. That's the way all of our light bulbs that are that screw-in kind work. Of course, there are other variants, like where you have two posts, you know, like those halogen light bulbs. You guys know the ones I'm talking about? They have like a couple of spikes, and you like just press them in, their friction fit in. No, there's not as many of those ones kicking around. There's one that has like a couple of knobs on the bottom that look like this. That's a style of light bulb. You push it in and then you twist it, kind of thing. But even those ones work the same way as this, where the electrons go in one post and out the other post, and there's a load in between. Okay, all of them working the same. But these electrons, here's a Coulomb of electrons going in. It goes in. Notice that it's got dots in it. These dots are loaded up with energy. This is the energy that electron is carrying. It goes in. It gets to the load, the LED, the filament, whatever. It unloads its energy at the load, and then it keeps on going. Notice that it's been depleted. It has no energy inside of it anymore. It keeps on going. And I think that one thing that people coming out of grade 9 don't get is the electrons don't get consumed. They go in one side, they go out the other side. The electron doesn't get consumed. The energy that electrons hold